Okay, welcome to another video of the study of the Hamilton-Jacobi formalism. Today we are going to look to another example of the use of the method of separation of variables to solve the Hamilton-Jacobi equation. And the example that we are going to look today is about a particle in a central field of force. We have been doing videos about the Kepler problem and central forces. In those videos, we showed that a particle that is under the influence of a central force, this particle is going to move on a plane. Okay, so its motion is only going to be in 2 dimensions. So looking at the motion is just in 2 dimensions, we can parameterize the motion of the particle with just 2 variables that are an angle theta and a distance r, like the polar coordinates. So for this example, we know that we are going to have a Hamiltonian that corresponds to this mechanical system equals to 1 divided by 2m times pr squared plus p theta squared divided by r squared, and then plus br, where br is this potential due to the central force. Or I should say that the force is due to this potential B. Remember that, these conjugate momentas, PR and P theta, they come from the definition of the conjugate momenta in terms of the Lagrangian. This means that PR is equal to the partial derivative of L with respect to R dot, and P theta is equal to the partial derivative of the Lagrangian with respect to theta dot. Okay, this comes from, the fundamentals of the Lagrangian formalism. So we can construct a Hamiltonian for this mechanical system given by this expression that I just wrote. Okay, and we remember that the structure of the Hamilton-Jacobi equation is that, we have the Hamiltonian H as a function of Qi, the partial of S with respect to Qi, and the time, and then plus the partial of S with respect to t, and this is equal to 0. Remember that here we take S as a function that is a generating function for a canonical transformation. This is the meaning that we have been giving to this S that we have here. And in this case, for our system, we see that we have 2 generalized coordinates. Of course, the first one could be maybe the radius, and the second one will be theta. Okay, so that means that this Hamiltonian actually corresponds to a system with 2 generalized coordinates. Perfect. So we see here that in this general form of the Hamilton-Jacobi equation, we are including the generalized coordinates as a variable from which the Hamiltonian has some dependence. But in our case, these generalized coordinates do not appear. I mean that we do not have the theta explicitly in the expression. So what we are going to do in this case is just to substitute these values of P with for the R variable and the theta variable. We are going to substitute these values with the derivative of S with respect to the corresponding variable. So that means that we are going to get that the Hamilton-Jacobi equation for the particle in the central field of force is going to be 1 divided by 2m, that is going to multiply, the partial of S with respect to R squared plus the partial of S with respect to theta squared, and then this this is divided by R squared, and then plus B of R equals and we need to add the partial of S with respect to time, that is here, and this is equal to 0. Look that where we have the place for the p's, we substitute those for the partial of S with respect to the q's. That is what the Hamilton-Jacobi equation is about. Perfect. Okay. So remember the method of separation of variables wants to propose a function that is going to be the sum of three functions that are of one variable. So that means that we can express this as a of r plus b of theta plus z of t. And also remember in the previous lesson that we mentioned that if some coordinate is not included in the Hamiltonian explicitly in the expression, well, that means that the function that corresponds to that variable, well, is going to be a linear function. So we can immediately see that b of theta and c of t, well, they are going to correspond to linear functions, because in our Hamiltonian we do not have the theta and we do not have the time explicitly. So that means that S is going to get the form a of r plus, let's say, p2 theta and then minus p1 t. This minus is because we usually take this function of time to the right hand side of the equation, and that is equivalent to minus the partial of s with respect to time. So to cancel this minus, we put this minus here. But it's not very important. The thing here is that p2 and p1 that later on will be matched with the conjugate momentas that correspond to the canonical transformation, well, they are constants. Okay, this will be important. These two things here are constants. Perfect. So we are going to take this function s and we are going to plug it into the Hamilton-Jacobi equation to see what are we going to get. Well, we see that we need to calculate the partial of s with respect to r, and that is, well, it is easy to see that the partial of s with respect to r is equal to the total derivative of a with respect to r. Then the partial of s with respect to theta is, of course, just p2, and the partial of s with respect to time is going to be minus p1. Perfect. So let me substitute this into the Hamilton-Jacobi equation to get 1 divided by 2m that multiplies, it will be here the derivative of a with respect to r squared plus this thing squared, which is p2 squared divided by r squared, and then plus b of r, and then this thing over here, which is minus p1 equals to 0. Perfect. So what we can do is to solve this equation for the derivative of a with respect to r. And if we do that, we are going to see that the derivative of a with respect to r is equal to plus minus the square root of 2m that multiplies p1 minus b of r minus p2 squared divided by 2mr squared. Okay, this is, well, the derivative of a with respect to r, and this leads us to the function a of r that is going to be equivalent to plus minus the integral of all these p's that we have here, like this, and then the r here. Okay, perfect. So it is very obvious that we cannot solve this integral because we do not know what is the form, the mathematical expression that represents this b of r. So we're just going to express the solution in terms of this integral. So that means that s is going to be equal to, and some other important thing is that, well, we just need to find one solution of the Hamilton-Jacobi equation. This is giving us two solutions, plus and minus. Well, we are just going to take the plus sign just for simplicity to express that the function s that we're looking for is the integral of this thing, dr, and then plus p2 theta minus p1 t. Okay, so this will be like the solution of the Hamilton-Jacobi equation, which again, remember that this s represents a function that is the generating function of a canonical transformation for this mechanical system. Another thing that is interesting to notice is that this function s is actually a function of all the variables that it can be: r, theta, p1, p2, and the time. Okay, so perfect. Okay, and remember that looking that s is a generating function of canonical transformations, s has to verify two equations that are going to be very important. The first one is that pi is equal to the partial of s with respect to qi. The other one is that qi, upper qi, is equal to the partial of s with respect to upper pi. Okay, so perfect. In this case, obviously, I goes from 1 to 2. So P1 is equivalent to PR. So this is telling us that PR is equal to the partial of S with respect to, it will be Q1, but remember Q1 represents the R. Okay, so to find PR, well, we may need to take the derivative of all this function with respect to R. But look, this quantity and this quantity do not depend on the R. So the partial of S with respect to R will make these two equal to 0. Another thing is that we have an integral with respect to the variable R. So if we take the derivative, well, we are just going to get the expression that is inside the integral. So that means that we can easily verify that PR is equal to the square root of 2m that multiplies p1 minus b of r minus p2 squared divided by 2mr squared. Okay, perfect. So this will be PR. Then we already know that actually, yeah, well, we know that this s, well, it is very trivial to calculate the partial derivative of this s with respect to theta. Okay, we are only going to get p2, upper p2. So that means that this p theta, which is the partial of s with respect to theta, is equal to upper p2. Perfect. So yeah. Okay. So that means that, well, p theta is a constant. Perfect. Okay. Another thing that we can do is to calculate the transformations Q1 and Q2. We see that Q1 will be equal to the partial of S with respect to P1. But what will that be? Well, we may need to take the derivative of all this with respect to P1. Okay, and yeah, well, to do that, we are going to take the derivative of the integral, but we are going to switch those operators to get the integral of the derivative of this whole thing with respect to P1. So we will get that this derivative is going to be the integral of the derivative with respect to P1 of the square root of 2m that multiplies P1 minus b of r minus P2 squared divided by 2mr squared dr, and then the derivative with respect to P1 of this, but that will be minus t. So we will get a minus t over here. Okay, so what happens if we calculate this derivative? We are going to get the integral of, we will get 1/2 times 2m that multiplies p1 minus b of r minus p2 squared divided by 2mr squared. All this is raised to the negative 1/2. And then, well, the derivative with respect to p1 of what is inside of this, but that will be a 2m, so we will get 2m here. And we have a dr here, and then minus t. So that means that Q1 is going to be equal to, what are we going to get? It will be, well, we can cancel these 2's to get the integral of m dr dividing 2m that multiplies p1 minus b of r minus p2 squared, 2mr squared here, and this all is raised to the 1/2. And then minus t, of course. So with this we get Q1. Perfect. So with Q2 we can do something similar. We know for the equations of canonical transformations for S that the partial of S with respect to P2 is equal to Q2. So yeah, we have this expression for S. We see that if we calculate the derivative of S with respect to P2, here we are going to get a theta, and then we need to take the derivative with respect to P2 of all this expression that we have here. So this is going to be theta plus the integral of the derivative with respect to P2 of 2m that multiplies P1 minus B of R minus P2 squared divided by 2mr squared, all these raised to the 1/2, and then dr. Perfect. So what are we going to get? This will be theta plus the integral of 1/2, and then this multiplies all that stuff, 2m P1 minus B of R minus P2 squared divided by 2mr squared. It will be raised to the negative 1/2, and then we are going to take the derivative with respect to P2 of what is inside. But what will that be? Well, if we multiply this 2m with this expression, we are going to get just minus P2 squared divided by R squared. So the derivative with respect to P2 of this is going to take us to minus 2P2 divided by R squared. So that means that we need to multiply here by a factor of minus 2P2 divided by R squared. And then here we have the dr. Perfect. Okay. We see that these 2 cancels with these 2, and we are going to get here theta minus, looking that P2 is a constant, we can take it out, and this is going to be the integral of, we will get here a dr, and then this is dividing on R squared, that is going to multiply 2m P1 minus B of R minus P2 squared divided by 2mr squared, all raised to the 1/2. Okay, perfect. So this will be the final value of Q2. Perfect. And if you have seen our other videos talking about central forces and the Kepler problem, you will identify these equations as the equations of the orbit of the particle that is under the influence of the central force. Okay? Just remember that to be able to find the complete orbit, well, we need to give some values of the potential energy B of R, because in this manner we are not able to solve these integrals. Okay, and well, these are the values for Q1 and Q2, but we have already found the values of P2 in terms of the little variables. Remember that was, I can find it, yeah, it is here. P2 is equal to P theta. Okay, so that will be another part of the canonical transformation. And well, we still need to find an expression for P1 in terms of the little variables. So, well, that will be easy. We have that P1 from this equation that we have here, this one. We know that, well, we can solve this for P1, and P2 is P theta. So that means that if we solve this for P1, we will get a function that is only in terms of the little piece. So if we solve that equation for P1, we will get that this is 1 divided by 2m times PR squared plus P theta squared divided by R squared plus B of R. That, look, it is actually equal to the Hamiltonian of the system. So very curious. And it is actually something that we should expect, because remember that the Hamiltonian, it is a constant of motion. If you take the derivative with respect to time of the Hamiltonian, it is equal to 0. which means that this Hamiltonian is a constant of motion, and that P1 is also a constant of motion. So yeah. Another thing we can mention is that this P2 that we found, where is it? Well, looking that it is equal to P theta, it corresponds to the angular momentum, okay? This P, remember, it represents the conjugate momenta, but looking at the variable here is the theta, well, this corresponds to the angular momentum of the system. Perfect. So with this, we have just found first the solution of the Hamilton-Jacobi equation, and then found what are the canonical transformations that correspond to the function S, that is the solution of the Hamilton-Jacobi equation. So let's just finish the lesson right now.